Talk about our differentials. Which kind of tied in here because of linearization and so forth. We're talking about the tangent line. Recall we defined, if you will, a differential dy in 2 dimensions to be the derivative with respect to x of f times dx. Okay. And really all that comes from is the fact that, you know, the derivative is the slope of the tangent line, and the slope of the tangent line we could also rise over run dy dx. And so we get all that. You know, if here's your x value, then what we're talking about, the dx, just a small amount of increase from the x, so that's dx. And so then dy, you're talking about your slope of your tangent, so that's dx, then this is dy, isn't it? All right. And the other quantities we mentioned there is delta x and delta y, which how are those tied in? Well, delta x is a change in the x, so that's just going to be the same as dx. The delta y is a little different because we're going from this point now to this point, and so the change in y, the delta y is a little bit different, but you know, again, if you get smaller and smaller dx, then your delta y and dy are very, very close. Well, so when we go to 3 dimensions, z equals f of xy, let's call it. Pretty much the same, except your differential dz, it's called the total differential. Since you've got 2 variables, independent variables, guess what you got to use? Partial derivative, okay? So you can do the partial derivative of x, xy times dx, so that'll be times your differential dx, plus then the partial with respect to y, xy, that'll be your d times your dy. That'll give you the differential dz in 3 dimensions there. And again, very analogous. The dx is, you know, how far out in the x you go. Dy is how far out in the y you're changing. Then, of course, dz is the change in the height, the overall height there. Okay. So just one of those. See how it all works. All right, so find dz for z equals x squared plus 3xy minus y squared. So again, dz, partial f with respect to x of xy times dz plus partial of y, xy, oops, dx. Blah. All right, so again, you just need the partials. Partial of f with respect to x. What's that going to be? 2x plus 3y. And the partial of y with respect to, partial of f with respect to y would be 3x minus 2y. because the x is constant, so that would be 0. And there you go. All right. And so that would just, we're just plugging them in. We don't have numbers here, so it'd just be 2x plus 3y for this times your dx plus the 3x minus 2y times the dy. All right, so if, here's the second part. If x changes from 2 to 2.05 and y changes from 3 to 2.96, first of all, what is dz? dz would be, all right, so what's my x and my y? The x and the y are just where you start. So we started at 2 and 3, right? So x is 2, y is 3, so it would be 4 plus 9 times dx, which is a delta x. Yeah, dx equals delta x. So that's just the change of x. .05. And all right, so we get 6 minus 6. And then in this case, what's dy? Well, now that's our independent, yeah. So dy and delta y are going to be the same. Because that's just the change, how much we're changing the y. So that would be, the change in the y would be negative 0.04, which is not going to matter because that's 0. Okay. So that's dz equals 13 times 0.5. 0.05 plus 0. So it's what? 0.65. Now, dx, delta x, dy, and delta y are the same, but dz and delta z are going to be slightly different, right? So what about delta z? What is delta z? Yeah, delta z is just the difference of the second x value, y value, minus the first x value, y value. So that would be f of 2.05, comma 2.96 minus first x value is 2.3, right? Yeah, 2.3. What, 2.05 squared plus 3 times 2.05 times 2.96 minus then, so that's the first one. Then the second one is, have we done that yet? I don't think so. Second one we plug in 2, so we get 4. So it'll be 2 squared plus 3 times 2 times, going back to this one now, 3 times 2 times 3 plus, minus 2.93 squared. .05 squared. .6449. Oh, we're pretty close. All right.